Question 49 has quite a few crucial variables and is a complicated question to visualize. In spite of this complexity, it deals with a relatively straightforward process and HVAC concept, so clear thinking can give you the solution. Initial critical thought solution elements. 1. What are you solving for? The temperature of water leaving a cooling tower. 2. What is the fundamental process? A perfectly balanced, steady flow heat transfer for both air and water. 3. What are the first considerations to find the solution in connection to the fundamental process? Setting the scene in your imagination in order to simplify how and why the heat transfer is happening. 4. Are there key assumptions? Sea level altitude, standard air and water conditions, steady flow energy transfer, and an ideal motor. The purpose of a cooling tower is to take heat from a refrigeration cycle and reject it out into the atmospheric air. A simple knowledge of refrigeration cycles will indicate that cooling towers are always used on the condenser leg of the cycle. The evaporator pulls heat energy into the refrigeration cycle from the air used by the air handling system to cool a space. That heat energy is later expelled out of the refrigeration cycle by the condenser to balance the whole cycle. What heat comes in must go out. The condenser can use many different ways to expel the heat. In this case, it's using a cooling tower, which is very common. No detailed information about the condenser is given, and the analysis should only be focused on the cooling tower. The generic circumstance given in this question might be illustrated like this. It could also be illustrated with a differently configured cooling tower. This shows an indirect contact, closed-circuit cooling tower. There are others, such as vertical spray, direct contact, or open evaporative cooling towers, but this will work for the purposes of question 49. The question is not concerned with losses of the water sprayed in the cooling tower, which is called drift or blowdown. These sorts of losses would be considered makeup water requirements. It is important to note, if you search for any analysis on cooling towers in the NCEES Mechanical Reference Handbook, version 1.1, you will only find discussion on the topic of calculating makeup water requirements, which, incidentally, is in section 9.3.9.2. You will not find any help for the analysis needed in this question, number 49. So while there will be water used here, you should be focused on the water from the condenser, used here. It's this exiting water temperature that you are supposed to solve for. Cooling tower analysis links steady state energy flow of the air, which flows here, with the water, which flows here. The key critical thinking element for this cooling tower is balance. Energy that flows in must flow out. Nothing simply disappears. You should have these 4 energy flow equations memorized for the PE exam. You'll need to use them very frequently. You're given entering and exiting air conditions. These indicate that the energy which is transferred to the air is in the form of humidity and not dry bulb temperature. The energy flow equations for air are these 3. With no change in dry bulb temperature, you will not use the sensible heat transfer equation. Though the solution given by the NCEES uses the total heat transfer equation, you can use the latent heat transfer equation because, as we already said, the change in the air conditions is purely humidity. look up the humidity ratio in the sea level psychrometric chart for both the entering air and the exiting air. The humidity ratio for 85 degrees Fahrenheit dry bulb air at 50% relative humidity roughly equals 0.0129. And for 85 degrees Fahrenheit dry bulb air at 80% relative humidity roughly equals 0.0210. The air flows at 112,250 CFM. So with this data, you can determine the heat energy that the cooling tower is rejecting out into the atmosphere, which is 4,400,650 BTU per hour. Because the process is steady flow, you might be tempted to assume that this is the total amount of heat taken from the condenser water. But when a motor is inside the airflow, it contributes its heat to that airflow, a circumstance frequent for cooling towers. In the NCEES Mechanical Reference Handbook, version 1.1, in section 9.1.4, you can find the equation for applying the heat energy created by the motor to the airflow. No data is given in the question about efficiency, use factor, or load factor for the motor, so assume these are 1. This means a simple equation, which is essentially a conversion from brake horsepower into BTU per hour. This is the amount of heat energy contributed to the exiting air which is not taken from the condenser water. When you subtract that heat energy, you are left with the actual amount taken from the condenser water. Use the fourth energy flow equation from this list, which is the one for water, to determine the temperature difference. Take that delta T away from the entering water temperature to find exiting temperature. The solution is roughly 88 degrees Fahrenheit. It's worth noting that when you're doing this, you're solving for what is technically called the range, that is, the delta T of the water cooled by the cooling tower. Another key term for cooling towers is the approach. That's the difference between the entering air temperature here and the exiting water temperature here. To get good at questions like this, study ASHRAE HVAC Systems and Equipment, Chapter 40, Cooling Towers. In the ExOverZero practice tests, do problem number 50 in tests 1, 2, 3, and 4.